For what class? For lunch. And the food to be. So in the campus. One every week. Two in the same day, one day. What is it? This structural analysis and then environmental engineering and oh, yeah.
I have a question.
Yeah.
What a short answer, short question
Yeah.
answer on your midterm exam.
Yeah.
It's the same. Are there same as a question on the
On the home. Not exactly the same, but same style.
Oh.
Yeah. Mhm.
I just left the first part, third column, on the first question, on the other speed, the first part, the other question, that part, getting answered, I don't know, rest of it, and then the other one was like, I had the phone call. And then that was said, so, you know, I just, I definitely the book, and I just started Control F, it's bro, because you want to log into your history. I didn't want you to get anything over that one. You just search it, title of the Wikipedia, and then. Yeah, and I just control that. The fact that it's open notice. Free. But the questions were hard, like, she isn't lecture enough to be asked some questions and all that.
I know.
But still going to be like, simple, like, right?
No,
I think I was. Yeah.
you got her test.
I was really fun to work.
How was it?
That class is amazing.
She said the whole.
Because I feel
No way.
the way she lectures and like presents the slides. And then the types of questions she asks is actually. I feel like she expects us to already have knowledge of that.
Yeah, that was the class I thought. Our class I was like,
She has like these crazy questions that aren't even on the slides.
so like, she's in.
I want to do the slides,
It's gonna
and I
be
couldn't find any confirmation. It's the first question.
We don't know. Everyone's like.
I knew it was over everything and there's nothing.
It's like.
Yes. I was. Or,
Yeah, that's funny. Because we was like, oh,
Is that one? Yeah, that's the one that.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, busy week, I'm sure. You guys, it sounds like you guys have midterms this week, so and we have our midterm next week. So just a reminder, our midterm is next Thursday. So I did just write to the exam yesterday. So it's fully written. So you know, you can you know, not, there won't be any surprises on the exam. I guess I'll say that. Okay, so everything is gonna be on the exam that's on the study. All right, so today, I'm hoping today is gonna be the last day that we talk about Laplace. So I have just a couple examples to go through today. An example with step functions and an example with impulse functions, and we have to kind of talk briefly about what impulse functions are. So after today, you know, today's going to be the last day that we cover this stuff. After today, you know, we're going to be moving on to other stuff. Okay. All right. So announcements. So I know there's some mistakes on my solutions on the homework, particularly problem 3. So I apologize for that. I said that I would take care of it yesterday, but I had some things come up yesterday, so I couldn't get to do it. So tomorrow I will fix those solutions for problem 3. I believe it's problem 3B and 3C that there are issues with the coefficients. So I see the issues, but I just haven't had a chance to just fix them. So but I will do that tomorrow. Okay. So for now, you know, if you're working through the homework, just, you know, I would trust your gut with 3B and 3C. You're probably correct. And then, you know, you can wait for my updated solutions tomorrow. Okay. Also, I don't remember if I said this on Tuesday, but I did post the solutions for homeworks 1, the fully worked out solutions for homework 1 and homework 2 onto Canvas. And so definitely check those out just to help you guys study. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's pick up where we left off. And so I'm just going to scroll up a bit. So we left off last time working on this example here. Okay. And so, you know, we've been talking about Laplace transforms all this time. And, you know, the main reason we're going through Laplace is to be able to solve differential equations like this, right? So we have a fairly simple differential equation, y double prime plus 4y is equal to g of t, okay? So what's unique about this is that our forcing function g of t is discontinuous. So it's had a kind of a piecewise definition there. So from t is equal to 0 until t is equal to 5, our forcing function 0. Then at t is equal to 5, we start ramping up with the function t minus 5 divided by 5. And then when t is greater than 10, we just even out at 1. Okay, so this is a fairly typical case, a very typical engineering case where you have a function that kind of ramps up and then kind of evens out. But we can't really solve this with our traditional methods. Or we can, it's just a lot more trouble to do so because we'd have to solve, well, in this case, we'd have to solve two different problems. And then you would go from there. Okay. Okay. So the steps that we're going to take to solve this function is, or to solve this problem is listed out here. So step one, we're going to represent our forcing function g of t using step functions. So that was kind of the last thing that we did in class on Tuesday, right? So that's kind of what we did at the bottom there. Step two is to take the Laplace transform of this, keeping in mind the Laplace transform of all of these step functions as well as the base functions. We're going to need to apply some t shifting here as well in order to get everything to match up. Okay. Then from there, we use our typical kind of Laplace kind of methodology here. We take the Laplace transform of the entire differential equation. We solve that expression algebraically for y of s, and then we take the inverse Laplace of that entire thing, possibly using partial fractions along the way to simplify those expressions. Okay. Okay, so for today, I wanted to kind of just get started with this example right away, but that was just kind of a recap from last time. Okay, so the step function representation of our forcing function is at the bottom of the screen here. And so first we have the section from t is equal to 5 until t is equal to 10. And so we have our function t minus 5 divided by 5. And we're going to multiply that by the difference between two step functions. So first we have u of t minus 5, because this is when that portion starts. And then the time where it ends is the second part right here. So this is at t is equal to 10. Okay. So when you're constructing these kind of forcing functions here, you have to just kind of be aware of when the certain parts start and when the other parts end. Okay. Now for the second part of the forcing function, when g of t is equal to 1, this one doesn't have an ending time. So this one's just going to persist for all time, starting at t is equal to 10. Okay. And so to represent that with a step function, we have plus 1 times u of t minus 10. Okay. Okay, so let's move on to step 2. So step 2, we are going to take the Laplace transform of that expression. Okay. So let me write down g of t here just so we can work on it. So we have g of t is equal to t minus 5 divided by 5 multiplied by u of t minus 5 minus u of t minus 10 plus u of t minus 10. Okay. So first thing I'm going to do here, let's go ahead and distribute the t minus 5 into into that square wave. Okay? I'm going to keep the 1/5 on the outside just because it's just going to clutter our space. But I'm going to take that t minus 5 on the interior. So we have 1/5 t minus 5 times u of t minus 5 minus t minus 5 u of t minus 10 plus u of t minus 10. Okay, so now we're going to take the Laplace transform of all of these terms here. So we're going to end up with g of s is equal to 1/5 times Laplace transform of the quantity t minus 5 u of t minus 5 minus Laplace transform of t minus 5 times u of t minus 10 plus Laplace transform of u of t minus 10. Okay. So, just like we usually do, we're making use of the linearity property of the Laplace transform and just applying it to each individual expression in our okay. Okay. Good. And the 1/5 is just kind of just along for the right. All right. So let's go ahead and take these Laplace transforms. So luckily, most of these are going to be good. Okay. So let's start from the left. So here we have the Laplace transform of the function t minus 5 times u of t minus 5. So since we have a shift here, so since this step function is telling us we have a shift of 5, right? That means in order to take its Laplace transform, we have to apply a t shift, or our second shifting theorem. Okay. But luckily for us in this case, our shift is exactly the same, both in the step function and in the base function. So both t minus 5 and u of t minus 5 have the same shift. Okay. And so in this case, there's nothing, we just have to apply the second shifting theorem straight up. And so to apply the second shifting theorem straight up, we're going to have e raised to the minus 5s, okay? Because we have a shift of minus 5, and so we multiply that by e to the minus 5s when we take the Laplace transform. And then we're going to shift everything, the base function by 5. So we're going to add t plus 5. Okay? And so from that, we're going to take the Laplace transform of t. All right, so the Laplace transform of t is fairly simple. We can look that up in the table. Okay. And so we get e to the minus 5s all over s squared. All right, so that's the Laplace transform of that first term. All right, any questions on this so far? Yes.
Can you explain again the shift of 5?
Yeah, for sure. So so in order to determine kind of what shift that you have to look and see what's inside either the step function or eventually the impulse function. So you're gonna look at the special function. And so since the special function in this case is a step function and it's u of t minus 5, that tells us that we need to perform a shift of 5 when we perform the Laplace transform. Right? Okay, so we know just by looking at the step function that we have a shift of 5. So we basically need to apply that shift to our base function. And our base function in this case is just everything that's multiplied by it, which is t minus 5. Okay, so to apply the second shifting theorem, you're basically going to multiply. The first thing you're going to do is you're going to multiply by an exponential term in the Laplace domain that has that shift. And so since we have a shift of 5, we're going to multiply by e to the minus 5s. Okay. And then you're going to apply that shift of 5 to your base function. And so since we had a shift of 5, we're just going to add 5 to t there. Okay. So the way I got this t right here, it was actually t minus 5, which is our base function, plus 5, and this plus 5 came from the shift. Right, and so we have t minus 5 plus 5, the plus 5 cancels out with the minus 5, and that's why we just get a Laplace transform of t, and then Laplace transform of t is 1 over s squared. Okay. So we're going to do the exact same thing for the second term there, because the second term we have a shift as well. But in this case, if we look at the shift, we have a shift of 10 in this case. Okay. So once again, we're going to apply our second shifting theorem. But this time, the shift in our step function does not match the shift in the base function. Okay, so we have different shifts here. So that means, when you take the Laplace transform of this, you're probably going to have some extra term because of that difference in the shift. Okay? But we can do exactly the same thing we did in the previous part. So let's multiply this by, well, we have a shift of 10. Let me clear out some of this here, just so we can see. Okay. And so since we have a shift of 10, I'm going to multiply this by e to the minus 10s. Okay. That's our second shifting theorem at work. And then from there, we're going to do our modified second shifting theorem that we introduced on Tuesday. So we're going to take the Laplace transform of our base function, so t minus 5. And then to that, we're going to add our shift. And so we have a shift of 10. And so we're going to add 10 to this expression. All right, I know the signs can be kind of confusing, and whether you add or you subtract, it's a lot to keep track of. But the thing to remember when you're doing the modified shifting theorem is that when you apply the shift, you end up with an exponential of the same sign, right? So since we have a shift of minus 10 in the step function, that means we're going to multiply by e to the minus 10s, okay? And so that already kind of takes care of that shift. But when you apply the shift to the base function, you're going to use the opposite sign. And so since we did a shift of minus 10s up there, when we apply it to the base function, we're going to add 10 to it. Okay, and if you're ever not sure what direction that you should look at, you can kind of make you kind of do a sidebar and think, okay, what if the shift was the same? So in this case, it's clear to see in this first part that t minus 5, u of t minus 5, these shifts are the same. And so when you apply the operation of the modified shifting theorem, those shifts should cancel out. Okay. So that's kind of your sanity check. So, if you're not sure whether you should add 10 or subtract 10, like we did in that other one, pretend and see, what if that shift was the same? So, if I add 5 in this case, is that going to cancel out? If not, if it's just going to make it worse, then, then you should do the opposite. Okay. So with so many rules and so many kind of weird things, it is very easy to kind of get tripped up in the sign. I still do it, as evidenced by all the mistakes I made in the homework. But just as you're doing it, just kind of give yourself these sanity checks just so you. Okay. So after we apply that shift right there, we have e to the minus 10s. And so in this case, it's not going to cancel out. We're going to take the Laplace transform of t plus 5. Okay. All right. And we can take the Laplace transform of each of these individuals. So we have a Laplace transform of t, which is 1 over s squared. And then we have the Laplace transform of 5, which is 5 divided by s. And this entire thing is multiplied by e to the minus 10s. Okay. All right, any questions on this part here? Okay, good. All right, and then the last term that we have there is just an Laplace transform of u of t minus 10. This is the simplest one to do. This is in the table. Okay. But I guess technically speaking, you can apply second shifting theorem and then take the Laplace transform of 1. That's basically the same thing. But, in this case, you can just read it off the table. Okay. And so Laplace transform of this, you just draw an arrow, is going to be e to the minus 10s divided by s. Okay, so let's go ahead and put this all together. And so this is all going to form the Laplace transform of our forcing function. Okay, and so we put it all together, then our g of s is equal to 1/5 e to the minus 5s divided by s squared plus e to the minus 10s times 1 over s squared plus 5 over s plus e to the minus 10s over s. Oh, sorry, this is a minus sign here. This is why I keep making mistakes. I keep missing signs like that. Little sleep deprived. I forgot I was supposed to give my buddy a ride to the airport. He arrived at my home at 7:30, called me and woke me up. He's like, "I need you to take me to the airport." I'm like, "Oh, I forgot." Okay, so that's step 2 of the problem. And so now that we have the Laplace representation of our forcing function here, we can now incorporate it into our differential equation. Okay. Okay, because step 3 of this problem is to take the Laplace transform of the entire equation. And by equation, I mean the differential equation. Okay, so our differential equation in this case was y double prime plus, or y is equal to g of t. Okay, so let's go ahead and take the Laplace transform of this entire expression here. Okay. Okay, and so we take the Laplace transform of y double prime, we get s squared y of s minus s y of 0 minus y prime of 0 plus 4 y of s is equal to g of s. Okay. Where g of s is the expression that we just found in the previous part, right above this, which is conveniently cut off on the screen. Okay. So g of s is just this guy here. Okay. So let's go ahead and plug in the initial conditions to this to simplify this expression. I believe for this problem, we assume the initial conditions were 0. So from the problem, y of 0 is equal to 0, y prime of 0 is equal to 0. And so that's going to cancel these out. Okay. And so we have s squared plus 4 times y of s is equal to g of s. Okay. At this time, let's go ahead and plug in our expression for g of s. So g of s we know is 1/5 multiplied by e to the minus 5s all over s squared minus e to the minus 10s over s squared minus 5 e to the minus 10s over s plus e to the minus 10s all over s. Okay. And luckily for us, I didn't see this a second ago. But we do actually have some simplifications in g of s, because if you notice, we have a minus 5 e to the minus 10s over s. And that's multiplied by a 1/5 out in front, so that's going to cancel out with this 5, okay? And then we also have a plus e to the minus 10s over s as well. So both of these conveniently are going to cancel out. Should have noticed that earlier. And so if we solve for y of s, which is step 4, what we get is y of s is equal to 1/5 multiplied by e to the minus 5s all over s squared times s squared plus 4 minus e to the minus 10s divided by s squared times s squared plus 4. Okay. We have two fractions here, and so neither fraction is able to be inverted straight up. And so we have to perform partial fractions on this. Luckily for us, the two fractions are exactly the same. The only thing different is that they have different shifts. Okay. All right, so when we perform partial fractions, the shift is not really going to affect the partial fractions. And so we can just perform the same partial fractions for both and just kind of apply them up there. Okay, so next step, we're going to do partial fractions. Any questions on how we got to this point here? Okay. All right, so let's apply partial fractions here. So our partial fraction decomposition is going to be, we have 1 over s squared times s squared plus 4. Okay. And so we're going to decompose this. And so we have a repeated root here of s squared. So that's going to be a over s plus b over s squared plus cs plus d over s squared plus 4. Because the s squared plus 4 is a root or is a quadratic that we can't factor any further. So we have to kind of break it up into cs plus d. All right, so just like we usually do with partial fractions, let's go ahead and multiply this entire expression by the denominator. And so we're going to multiply this entire expression by s squared times s squared plus 4. Okay. And so if we do that, we get 1 is equal to a times s squared plus 4 plus b times s squared plus 4 plus cs plus d times s squared. All right, so let's go ahead and group the like terms and then set them and then kind of form our system of equations. Okay. And so you have 1 is equal to, we have s cubed. So the s cubed terms here, we have a and we have c. Okay. All right, then we have the s squared terms. So we have s squared, which is a b plus d. Okay. Then for the s terms, we have 4a plus, I think that's it. Yep. And then we have the constant terms. The constant term is just 4b. Okay. 1, 2, 3, 4, 6. All right. So let's go ahead and form our system of equations here. So we have s cubed, s squared, s, and 1. Okay. Let's start from the bottom. So from the bottom, we have our constant term. We do have a constant term on the left-hand side, which is just 1. And so that's going to be equal to 4b. Okay. So this tells us that b is equal to 1/4. Okay. For the s term, we only have 4a on the right-hand side. On the left-hand side, we don't have any s's. And so you have 0 is equal to 4a. This, of course, tells us that a is equal to 0. Next, we have the s squared terms. Left-hand side, we don't have any, so that's going to be 0. On the right-hand side, we have b plus d. Based on our solution for b, we know that b is equal to 1/4. In order to satisfy that equation, d must be equal to minus 1/4. And then finally, we have the s cubed term. And so s cubed on the left-hand side is 0. On the right-hand side is a plus c. Okay. But since we know that that a is equal to 0, that means c must also equal 0 as well. Okay. And I'm paranoid because all the mistakes I've been making on the homework is because of this, and so I'm just kind of paranoid, making sure I got all the coefficients correct in this case. Okay, good. I think these all look good. Okay, so we put this together, then our partial fraction decomposition is going to be, we have 1 over s squared times s squared plus 4 is equal to 1 over 4 s squared. So that's our b term. And our d term is a minus 1 over 4 times s squared plus 4. Okay. Now let's take this result and combine it together with y of s that we had above, and then we'll finally be able to take the inverse Laplace of our expression. Okay, and so if we integrate this, we have y of s is equal to, we have e to the minus 5s divided by 5 multiplied by 1/4 s squared minus 1 over 4 s squared plus 4. Okay. And then we have minus e to the minus 10s, I believe. Yep. E to the minus 10s divided by 5 times the same thing. So 1/4 s squared minus 1/4 s squared plus 4. Okay. All right. So now that we have in this form, we are ready to take the inverse Laplace because we have 1 over s squared that is in our table, and we have 1 over s squared plus 4 that is also in our table. That is just sign. Okay. All right. But I'll pause here. Any questions on how we got to this point here? Okay. All right. So now we're ready for step 5. Step 5, we're going to take the inverse Laplace. Okay. All right, and so we're going to do this in 2 phases. So remember, we have some shifting here. So we have some t shifting. So first, we're going to take the inverse Laplace of the base function, and then we're going to apply the shift to them. Okay. So now we are gonna have y of t. Okay, I'm gonna leave the shift alone because we're gonna apply the shift right afterwards. We have e to the minus 5s. Okay. First thing I'm gonna do, I'm gonna factor out a 1/4 and from each of those expressions just so we don't have to deal with it. And so if we factor out a 1/4, that's gonna multiply by the 1/5, and so we have e to the minus 5s over 20 multiplied by Laplace inverse of 1 over s squared minus Laplace inverse of 1 over s squared plus 4. And then we're gonna have the same thing for the other one as well. So we have minus e to the minus 10s all over 20 multiplied by the exact same thing. So we have Laplace inverse of 1 over s squared minus Laplace inverse of 1 over s squared plus 4. Okay. So let's go ahead and look at our Laplace table and apply these inverse Laplaces. So first we have Laplace inverse of 1 over s squared. This is just our function t. Okay. Then we have Laplace inverse of 1 over s squared plus 4. So that's going to be sine of t, sine of 2t. But we need the 1/2 out in front to balance out with the omega. So this is 1/2 sine of 2t. Okay. And then same thing we have over here. Laplace inverse of 1 over s squared. This is t. Laplace inverse of 1 over s squared plus 4. This is 1/2 sine of 2t. Okay. So let's go ahead and plug those in. So we have y of t is equal to e to the minus 5s over 20 multiplied by t minus 1/2 sine of 2t minus e to the minus 10s over 20 times t minus 1/2 sine of 2t. All right, we're almost done. Last thing that we have to do here is just apply our t shift. Okay. So the first term there, we have a t shift of 5, or it should be 20, excuse me. So we're going to replace, remember, to apply the t shifting, we have to do two things. So we have to replace everywhere that we see t, we're going to replace it with the shifted version. So we're going to replace it with t minus 5. And then number 2, we're going to multiply it by a step function with the same shift. Okay, so let's go ahead and do both of those things. We applied for the first term there, we have y of t. I'm going to multiply the step function by the outside just because we have the 1/20th there. So we have a u of t minus 5, okay, because we have a shift of 5. And then inside the parentheses here, we're going to replace every instance of t with t minus 5. So we have t minus 5 minus 1/2 sine of 2 t minus 5. Okay. And then we're going to do the same thing on the other term. So the other term with the shift of 10. So we have u of t minus 10 divided by 20 times 20t minus 10 minus 1/2 sine of 2t minus 10. And then finally, that is our solution to this equation. All right, that was a long example, just that there was a lot of steps involved. So this is our first time seeing step functions in an ODE. So I wanted to make sure I go through kind of every single step in the process. All right, any questions on this here? Yeah.
This, I'm sorry, go ahead. I was wondering, how did you get 1/2 sine?
So the 1/2 came from the inverse Laplace of 1 over s squared plus 4. So if you remember, actually I have it up here too. So the Laplace transform of sine is omega over sine squared s squared plus omega squared. And so in this case, omega is 2 because we have s squared plus 4. So 4 is 2 squared. And so in order for us to get the omega on top, we have to kind of divide by that same. Yeah. Any question two?
Yeah, it's more related to the exam.
Yeah.
I was wondering, like, how many questions are we gonna get on the exam? Because these are really lengthy.
Yeah, so something like this, you're only gonna get one like this. With step and impulse functions, there's just so many steps to them. I can really only ask you one, and that's probably gonna take you probably 20-30 minutes on the exam just for this one. So yeah, you're not gonna see more than one of these, but for the other ones, like first order, second order ODE, without any step and impulse functions, you may see multiple others. Yeah. Any other questions on this example here? Okay. All right. So last thing with Laplace before we kind of wrap up this this whole unit is impulse functions. Zoom in, zoom out a lot. Okay. This is the last topic here, but we've kind of gone through the hard part already. So step functions definitely are a lot more complex. Impulse functions, I think there's a little bit to it where there's a little bit of a kind of a intuition and conceptual knowledge with it. But how you actually use it in the equations is actually much simpler. You'll see. Okay. So what is an impulse function? So an impulse function is kind of very much the same thing as a step function, in that it's not a real mathematical function in the strictest sense. It's kind of an abstraction that we use to model certain kinds of behaviors. Okay. So an impulse function, just like step function, is a discontinuous function. But the role of the impulse function is quite different from the step. So an impulse function is meant to model something, some kind of forcing that happens very, very quickly. So it only kind of impacts your system for a very brief period of time. And so these impulse functions have a more formal mathematical meaning. So they're often called Dirac delta functions. At least that's kind of what I called it when I was in school, but that was kind of a while ago. So mathematically it looks like this. And so the symbol that we give impulse functions is some delta. Okay? And the delta is going to occur at some time of A, right? And so if you see an impulse function called delta t minus A, then at some time A, you're going to have the impulse, right? And so for all other times, the impulse function is 0, except at A, where it kind of goes up to infinity. And so if you want to kind of see a little bit kind of a stretched out, it kind of looks something like this. So all of a sudden A is going to shoot up, and then right after A is going to shoot right back down, just like that. Okay. So I've kind of exaggerated the width, and so it's not actually like that. So really, it's the width of it is kind of infinitesimally small. But that's kind of the idea, is that it's zero, it shoots up, and then comes right back down right after that. Okay, so if you were to shoot this mathematically, is a system turned on at that point? Yeah, I guess you can say it's very turned on at that point. Okay, so mathematically, delta t minus a is equal to infinity when t is equal to a, and it's going to be 0 at all other times. Which kind of seems ridiculous, right? So how can a function have an infinity value? Well, that's kind of why I told you the Dirac delta is not a real mathematical function. It's kind of a tool that we use for certain things. Okay. The more common way to use that you see the Dirac delta is usually in an integral. Right. And so if you take the integral from 0 to infinity of delta of t minus a, okay. So even though this Dirac delta function instantaneously has a value of infinity, actually the width of that spike is also 0. So you have kind of infinity multiplied by 0. And so if you try to take the area underneath the curve here, probably going to get something weird. But mathematically, the way that we reconcile this is that if you take the integral or the area of this curve, then you're just going to get 1. Okay, so it's a very weird function, but it has a very specific place, especially for us when we're modeling differential equations. Okay. Okay. So like I mentioned before, the impulse function is used to model situations with very brief, very kind of sudden kind of force. So let me give you some examples. Okay. So probably the most classic example, the one that I kind of use a lot, is running over a speed bump. So, if you're in a car, you run over a speed bump, all of a sudden, your car will be kind of smooth sailing, and all of a sudden your car will just kind of jump up when it hits that speed bump. Okay. But then after you're done riding over the speed bump, your car just kind of goes back to normal. Okay. And so in that situation, the speed bump it's applying forcing to your car, it's causing the car to react, but it only occurs over a very short period of time. Okay, number two. This is kind of more specific to mass spring dampers. And so what we can say is that if you take a mass spring damper and you just strike it very quickly with a hammer, and so you do what's called a hammer blow, that's also can be modeled using an impulse function. And that's very kind of common in practice as well. Okay. So one example that I saw just last night, I have 2 cats. I don't know if I mentioned before, but I have a toy that's like kind of a toy on a spring. And one of my cats just loves to just smack the hell out of it. So he'll smack it and the spring will kind of like go back and forth, and then he'll smack it again. So every time the cat smacks the toy, that's kind of like an impulsive function. Okay. And then another one, just because my background is in thermal fluids. And so when you have a combustion reaction, So you have kind of fuel and oxygen and air reacting and you ignite it. That's going to cause very sudden heating over a very brief period of time. Right, combustion is basically just pretty much like a controlled explosion. So, that explosion happens very briefly, the time scales for that, chemical reaction is very quick, but it is going to release a lot of heat. And so that heating from such a very quick phenomenon, we can consider that to be like an impulsive force. Okay. So Dirac deltas or impulse functions have a, they play a very important role. And so they allow us to basically mathematically model these systems into our differential equations. Okay. All right. Any questions on impulse functions so far? Okay. Let's talk about another property for impulse functions, which is what I call kind of function selection. So when you integrate an impulse function with another function, it actually picks out a value of that function from that interval. And the value that it picks out is going to be wherever the impulse took place. Okay. Okay. So for example, if you integrate from 0 to infinity of some function g of t, okay, and you multiply by the impulse function t minus a. Okay. So in other words, this is an impulse that occurs right at t is equal to a. The result of this is just going to be that function g of t evaluated at t is equal to a. So it's going to be equal to g of a. Okay. So this is a very unique, very kind of interesting property. So if we combine this with the Laplace transform, okay, we can obtain the Laplace transform of the impulse function. And so remember the Laplace transform is integral from 0 to infinity of e to the minus st. And we're going to multiply this by delta t minus a dt. Okay. Right, that's our mathematical formula expression for the Laplace transform. Okay. If we apply this exact same property right above to this Laplace transform, then we can see this is just going to be equal to e to the minus as. So in other words, we took our integrand, which is e to the minus st, and we replaced the value of t with the value of where the impulse took place. So we end up with e to the minus as. Okay. My pen is acting up right now. Okay. And this is in the Laplace table as well, but this derivation is super short. So that's why. All right, so this guy should look pretty familiar, this e to the minus as, because this is kind of the central component to our second shifting theorem. So what you're going to see is that once we incorporate impulse functions into our solution, we're going to end up with a lot of kind of shifted terms that we need to account. Okay. But the nice thing about this is that if you compare the Laplace transform of the impulse compared to the Laplace transform of the step function, Laplace transform of the step function had an 1 over s by it as well. Okay. But there's none of that here. So we don't have a 1 over s. And so we just have e to the minus as. And so what you're going to see is that taking inverse Laplace transforms with impulses is a lot simpler because you probably are not going to have to do any kind of partial fraction decomposition. Okay. Okay. So last thing I want to do today is I want to do a very quick example. This one's going to be much shorter than the previous one with an impulse function. Okay. Any questions on this before we jump into that example? Okay. All right. So let's go ahead and do it. Okay, so for this example here, let's look at a hammered load response to a mass for a mass spring damage. Okay. So we have y double prime plus 3y prime plus 2y is equal to delta t minus 1. Okay. So here we have an impulse function. That's our forcing function delta there. Okay. And we need initial conditions here. So let's keep things simple. So let's say that y of 0 is equal to 0 and y prime of 0 is equal to 0 as well. Okay. Okay, so we want to solve this equation. And since we have an impulse function on the right, we have to solve this using Laplace transforms. Okay, so let's go through our usual Laplace methodology here. So first, let's take the Laplace transform of the entire equation. All right, so we're going to take Laplace transform of the left-hand side. And so that's going to give us s squared y of s minus s y of 0 minus y prime of 0 plus 3 times s y of s minus y of 0 plus 2 y of s. Okay. Right-hand side is pretty straightforward. It's just delta t minus 1. And so that is basically just going to turn to a shift e to the minus s. All right, so let's plug in our initial conditions. This case is pretty simple. So our initial conditions, all of these terms are just going to go to 0 here. And so what we get is y of s multiplied by s squared plus 3s plus 2 is equal to e to the minus 2s. Okay. I'm going to go ahead and factor that left-hand side just because it's a quadratic. So you have y of s is equal y of s multiplied by s plus 1 times s plus 2 is equal to e to the minus 2s. Okay. So step 2, we're going to go ahead and solve for y of s.
Professor?
Yeah.
Where did the e to the minus 2s come from?
Oh, sorry, it should be e to the minus s. Thank you. Yeah, thanks for catching that. All right, so let's go ahead and solve for y of s. We have y of s equal to e to the minus s over s plus 1 times s plus 2. All right, and so before we can invert this, we have to take partial fractions, but this one's not so bad because we just have two terms here. We have an s plus 1 and an s plus 2. Okay, remember, we have that e to the minus s there. That's just going to be, that's eventually going to cause us to do a shift on the final solution. But when we do partial fractions and inverse Laplace, we can just largely ignore it. Okay. Okay. So if we do partial fractions, we have 1 over s plus 1 multiplied by s plus 2. Okay. Is equal to a over s plus 1 plus b over s plus 2. Right. So let's go ahead and multiply everything by the denominator. Right, and so we do that, we get 1 is equal to a times s plus 2 plus b times s plus 1. Okay. Let's go ahead and distribute and group like terms. And so you have 1 is equal to s, and then this is a plus b, and then plus constant term multiplied by 2a plus b. Okay. So let's go ahead and set up our system of equations here. So we have a plus b, our s terms. This is going to be equal to 0. And then our constant terms, we have 2a plus b is equal to 1. All right, and then from the first equation here, we have a is equal to minus b. Right. So let's go ahead and plug that into the second equation here. And so plug into the second equation, we have 2 times minus b plus b is equal to 1. Okay. We solve this, we get minus b is equal to 1. That means b is equal to minus 1. All right, and then if we plug that back in, the first equation, we get that a is equal to 1 in this case. Okay. Okay, so those are our coefficients, and so what we get is y of s is equal to, we have still our e to the minus s, but then now we're going to multiply it by, we have a, so that's 1 over s plus 1 minus 1 over s plus 2. All right, any questions on this so far? Okay. All right, so now now that we're in this position, we can go ahead and invert this. And so, you know, we have a shift here, so we have that e to the minus s. So first thing, let's invert the base functions. Okay. And then we'll apply the shift. Okay. So we have y of t is equal to e to the minus s. Okay. We have inverse Laplace of 1 over s plus 1. And so inverse Laplace of that is going to be e to the minus t. Okay. Minus inverse Laplace transform of 1 over s plus 2. And so that's going to give us e to the minus 2t. So those are obtained just straight from the table. All right, and then last thing we're going to do is just we're going to apply the shift, and the shift actually applies to both of these terms here. Okay, so when we apply the shift, we get y of t is equal to e to the minus t minus 1 times u of t minus 1 minus e to the minus 2 times t minus 1 multiplied by u of t minus 1. Any questions on this example here? All right, so generally speaking, with impulse functions, you're going to get problems that are typically a lot shorter than step functions, just because, also with impulses, you don't have things turning on and off, and so you just have kind of singular impulses. Okay, so this is not uncommon here. Okay, so we have about 10 minutes left. Let me do one more quick example with impulse functions. This one's actually quite similar to the homework that you guys are doing, so I think this is similar to problem 5 on the homework. At least mathematically. Contextually, it's not the same. So I think in the homework, it's like a stormtrooper shooting a gun. But this one's going to be slightly different. Okay, so in this problem here, we're going to look at a combustion chamber. So like I mentioned, a combustion reaction is basically just like a controlled explosion. When combustion takes place, it's going to ignite. It's going to give a really sudden big burst of heating, and then it's going to dissipate. Right. So it's kind of the perfect candidate for an impulse function. Okay? So if we draw kind of a very simplified version of a combustion chamber. Okay. So I'm just drawing a box around the combustion chamber. Okay, so let's assume that inside this chamber right here, we're going to have, basically a controlled explosion. Right. And so what that's going to do is that it's going to provide a very sudden heating through the combustion walls. Okay. Right, so the symbol that we have for heat transfer is Q, and so from the combustion reaction, that's going to provide a sudden burst, Q combustion. Okay. And then on the outside of this chamber, let's assume that we have an air that's cooling it down. Okay, we have sudden heating from the combustion reaction, but then we have steady cooling from the outside. So in these situations, when you have cooling or heating up by some kind of moving fluid, this is a phenomenon known as convection. So convection, if you haven't taken heat transfer yet, convection is just cooling of an object by blowing air over. So if you think of just the phenomenon, let's say you have a hot bowl of soup and you don't want to burn the inside of your mouth, usually what you do is you blow on it to kind of cool it down. Or if you've ever stood outside on a cold, windy day, the fact that wind exists will make it appear colder than it is. So all of that is convection. Okay. Okay. So what we want to do, so let's say in this problem, we're interested in the temperature of the chamber itself. Okay. So we're going to model the temperature of the combustion chamber using a differential equation. And luckily for us, convection cooling is a first order differential equation. It's not second. Okay. Okay. So it's been a while. We haven't seen a first order equation in a while. Oops. So let's say this is equal to dt plus h times t. Okay. So dt, kind of a mouthful to say, but that's basically the time rate of change of the temperature. H here represents what's called the convection coefficient. Okay. And let's say that, you know, we're applying heating from the combustion reactant. So the way we're going to model that is with an impulse function. And so let's say this is equal to delta T minus 3. So we're going to say that the combustion reaction occurs at T is equal to 3. Okay. Right, let me do this too. So this is not in the notes, but just a slight modification. You know, just because combustion reactions is very big. So we'll say that, you know, it's the exact function is 100 times delta T minus. Okay. That 100 is not going to do anything. It's just going to be passed along because of the linearity of the Laplace transform. But, you know, just to give this problem a little bit more freedom. Okay, and then just to keep things simple, we'll say that T of 0 is equal to 0. So we're going to start with the temperature of you know, room temperature base. Okay. Okay. So let's go ahead and solve this equation here. So let's go ahead and take its Laplace transform. Okay, so we take the Laplace transform of this entire thing. We have S times T of S minus T of 0 plus H T of S is equal to 100 e to the minus 3s. Okay. The Laplace transform of the impulse function is just e to the minus 3s, and then we just pass the 100. Okay. We know from the problem that our initial condition here is 0, so T of 0 is equal to 0. And so if we solve for T of S here, so we have S plus H times T of S is equal to 100 e to the minus 3s. So let's go ahead and solve for T of S. And so we have T of S is equal to 100 e to the minus 3s divided by S plus H. Okay. Right, so thankfully in this case, there is no partial fractions required, so we can just straight up invert this. Okay. So we have a base function here of 1 over S plus H. And so that inverse Laplace is going to be e to the minus HT. So we have T is equal to 100 e to the minus 3s multiplied by e to the minus HT. Okay. So we haven't applied the shift yet. We just did the base function. So let's apply the shift. Okay. So to apply the shift on this problem, you know, we're going to just do what we usually do. So we replace T with T minus 3, which is the shifted version, and we multiply by U of T minus 3. Okay, so we have T of T is equal to 100 e to the minus H T minus 3 multiplied by u of t minus. Okay, so your homework problem 5 is similar to this. I believe it was a first order equation as well. I think the only difference is that in problem 5, there are multiple impulses. So you're gonna have to do multiple shifts. Okay. All right, any questions on this? Or questions? So we can use this equation instead of q double prime is equal to h delta t. So that's Newton's law of cooling. So that's something different. This is more specific to just the temperature itself. So we didn't solve a formula for the heat transfer. We're solving the temperature for the or equation for the temperature. Yeah. So that equation, this equation are different. Yeah. All right. So thank you guys for coming today. That's it from Laplace. And so after today, so we're going to have a lecture on Tuesday. But what we cover on Tuesday is not going to be on the exam. So today is kind of the cutoff for exam. Okay. So thank you guys for coming today. Tomorrow, I promise tomorrow I will go and fix the homework solutions on problem 3. Okay, so kind of stay tuned for that. Hope you guys have a good weekend, and I will see you guys next week. Joel.
Honestly, like, who's gonna do a lecture?
Yeah. I didn't know what to expect. I want to ask them, and I think those people come here, but I would literally. Well, that's all. I don't know. Obviously, my.
Bye, thank you.
But.
Thanks.
Good luck now.
When she said like. Said it was large, size. I was like, what's the most.